All right, so today we are continuing our discussion on looking at confidence intervals for population proportions, but when we have two populations. All right, so remember last time we talked about hypothesis testing when we're looking at two populations and when we're trying to find out what's happening in our populations. We have a claim about a population proportion. So whenever the claim discussed a population proportion, we went ahead and we did a hypothesis test. And how this is different than the previous chapter is that now we have two populations. So we have a sample from one group and a sample from another group. Okay, so for confidence intervals, this is what the formula looks like. And notice that we are not constructing a confidence interval on P, but we're constructing a confidence interval on the difference. Right, so it's a confidence interval on the difference. So P1 minus P2. So it's not a confidence interval on the actual proportion for your population, but it's a confidence interval for the difference in your two proportions. So just like before, we need a margin of error, and the formula for the margin of error requires that we have a critical value. Now, do you remember what table you would go to find a z critical value? Okay, good. Table A2. Now, the critical values in table A2, those are the ones that were fixed. They didn't change because we did not have degrees of freedom. So remember, we had at the bottom of your table A2, we had the common critical values. Let me just show you real quick here. Looking for the formula card. Here it is. All right, so I'm going to, if you have the formula card in front of you, I'm just going to remind you that if you're looking for critical values, table A2, you go to the very bottom, and these are our critical values for Z. So that's from table A2. All right, so that's what you're paying attention to. All right, so for this formula, the critical values are going to come from table A2, and the common critical values are listed in your table. And we also found them back in chapter 7. I showed you how to come up with these critical values. Okay, so here's our example. So we are going to construct a 90% confidence interval. And it's going to be an estimate of the difference between the two population proportions. So that's P1 minus P2. So it's a confidence interval, and it's for the population proportion. It's that difference between the two population proportions. Okay, so the information we have here comes from two groups. So the first group, we have workers. So I'm going to write it at the bottom. That's where I have more space. Okay, so we have the group of workers. And I'm going to call this my first group. So I must have an X1, an N1, and maybe even a P hat 1. All these are coming from that first group. Okay, so the question says, a survey of 436 workers showed that 192 of them said that it was seriously unethical to monitor employee email. So 436, that's our sample size. And then from that sample, 192 say that it's unethical to monitor employee email. Now, I can come up with the p hat from x and n. So remember that the definition for p hat was that it was x over n. Now we have two groups here, so you're going to have to tell me what group it's coming from. It's either the first group or the second group. So you just have to put a little 1 or a 2 to let me know whether it's the first group or the second group. Okay, so we could get a p hat if we know x and n. So here x is 192 and n is 436. So our p hat, which is a percentage coming from our sample, can be obtained by taking x and dividing it by n. Now I would rather you use the fraction because the fraction is the exact p hat. If I were to put that in my calculator and come up with the decimal, that decimal is just an approximation because eventually you have to round it. And so your rounded value is just an approximation. If you insist on working with decimals instead of fractions, then you should at least keep it to 5 or 6 places after the decimal. If you don't, then this will change your confidence intervals. Your estimate for the confidence interval is going to change it. So you have to be careful with rounding there. Okay, so we have the workers, and then it said that 121 senior level bosses were also surveyed. So our second group are the groups of the senior level bosses. And so that's our second group. So everything that I write here is going to have that subscript of 2. So x2, n2, and then p hat 2. 121 senior level bosses were surveyed, and 40 of them said it was seriously unethical to monitor employee email. So 40 out of the 121. Sample size is 121. So can we come up with the percentage on that? P hat is x over n, so that's 40 over 121. Again, you want to keep it as a fraction because the fraction represents the exact proportion. Okay, so the question here is we want to construct a 90% confidence interval for the difference between the two population proportions. So the difference, that's your P1 minus P2. We want a confidence interval for the difference. So on the left side, you're going to have a value, and on the right side, you're going to have some value. But the estimate is for the difference of those two population proportions. So P1, that's the proportion that represents the workers in your population. And P2, that's the proportion that represents the bosses in the population. Now I have to go back and make sure I'm checking all my numbers, so it looks okay. All right, so now remember what your formula had. You need the margin of error. So I'm just copying that margin of error formula that you see there. All right, so that's all I'm copying down. And I'm going to do that on a new page because it looks like I'm out of space. All right, so my margin of error is the z critical value, and then it's times the square root of p hat q hat. Okay, that's from our first group. And then over our sample size. And then you're going to have p hat q hat. This is from our second group. And then that's the sample size, the second one, your sample size. Okay, so let's see what I need here. I need to figure out what the critical value is. What in the problem gives me the critical value? Or what will help me find the critical value. It's not given to me, but there's something there that will help me find the critical value. All right, so the 90%, okay, that's what I was waiting for. Okay, so that 90%, that's what's going to give me my Z. You see the 90%? That's going to give me my Z. And you already told me which table to go to. It was table A2. And I think this is the one that I had copied, although I don't see it anymore. Here it is. Okay, so for a 90% confidence interval, it looks like my critical value is 1.645. That's from table A2. Remember, the critical values from table A2, the Z critical values, those are fixed. They don't change no matter what the sample size. Those do not change, right? The ones that do change are the ones from the t distribution and the chi-square distribution. Okay, so 1.645. That's what I'm writing down because the confidence interval was 90%. Now I also know p hat and q hat. And I think that storing those fractions in the calculator make it easy, but you may decide that they're not. Maybe you just want to use you might just want to type the fraction in, and that's okay. So you can decide, what's easier for you. In this case, just because I don't want to keep flipping from the calculator to the white screen too many times, I'm just going to go ahead and fill everything out, okay? But you could use the store feature in your calculator, just like we did for the test statistic from the other day. Okay, so just to remind you from the previous screen, p hat was equal to 192 over 436. And that's our from the first group, the workers. And then from the senior level bosses, that was 40 over 121. So I'm just reminding you what we had said from the problem. So that's where I'm getting them from, p hat 1 and p hat 2. Okay, so I just copied them down again just so we have them on this new screen. So then p hat 1, that's 192 over 436. So that's my p hat. What's q hat? Anybody remember what q hat is? All right, so q hat is 1 minus p hat, yes? Okay, q hat is 1 minus p hat. All right, so what I'm doing is I'm just plugging in into the formula. There it is. So I have my p hat 1 and my p hat 2 there. You just told me what q hat was. That was 1 minus p hat, so 1 over 192 over 436. And q hat 2, again, is 1 minus p hat, so just remember you're subtracting p hat. The denominator, we have n1 and n2. So my denominator here is 436, because that's our sample size for our first group. So you can just go back and check the problem. N1 was 436, N2 was 121. So 436 and 121. Okay, so that's what I'm going to enter in the calculator. Again, you can use the store feature on your calculator if you don't want to type in your fractions like that. but I just wanted to keep from having to come from, there's too many screens here to have to keep track of, so that's what I'm going to enter on the calculator. And that's just our margin of error. I'm going to go ahead and store my margin of error into the calculator and just use that. All right, so I am going to move you over to the calculator, and then you can see what we have. All right, so what you just saw is going to get, I'm just going to type that into the calculator. So right now you should see the calculator on your screen. Okay, so remember we had the 1.645, and that was multiplied by the square root. And this is what's inside the square root. It was p hat 1 times q hat 1. So p hat 1, that was that fraction. And that was 192. And I'm going to put that in parentheses just to make sure that it all stays together. 192 over 436. That was my p hat from my first group. And then I multiplied by my q hat. And remember, q hat from the first group was 1 minus. So 1 minus what I just typed in, which was 192 over 436. All right, so what you see on your screen right now, that's your q hat for your first group. It's 1 minus p hat. And then that was divided by your sample size for the first group, so 436. Okay, so that's the first part of your formula. It was p hat times q hat over your sample size, which is 436 for the first group. So I'm going to do that again, but now I'm going to use p hat q hat for the second group. So then plus p hat for the second group, I think that was 40, and I'm putting that in parentheses, 40 over 121. Notice how I'm keeping that in parentheses. So that's our p hat for our second group, times q hat, which is 1 minus p hat. So it's 1 minus what I just typed in. So that's q hat. And then I divide that by that sample size for that second group, and that was 121. Okay, so that's the second part of what's in the square root. I have to press to the right arrow key just to get out of the square root, and then I'm going to press enter, and that is considered to be my margin of error. Now, if you want to see what you just typed, I'm just going to go to second enter, and then you can scroll to the left or to the right if you want to go back and edit anything. But everything's in there. All right, so that's my margin of error. So it's a lot to type in. So if you want to store your p hat 1 and you want to store your p hat 2, then you have that option too. So if you didn't get that, then you want to make sure you've entered the right numbers in there. So p hat 1 is 192, so I would double check to make sure you've entered exactly what I've entered. So go ahead and do second enter, and then you're just going to have to make sure you check step by step. So 1.645 times. If you have the older calculator, it gives you 1 parentheses automatic when you do the square root. Then the first thing I entered here, that was my p hat for my first group. So I'm checking my numbers just to make sure I didn't make a mistake. That was 192 over 436. Notice that that's in parentheses. So go back and check all of the numbers you entered. That p hat gets multiplied by 1 minus p hat, which is your q hat. So that's where you see the 1 minus 192 over 436. Can someone confirm that you got the same answer as I did, just to make sure that I didn't make a mistake? Okay. All right, so what you're seeing on the on the screen right now, that's your Q hat from your first group. So if you didn't get the same answer, just make sure you check everything that you have here. So you had to divide by 436. That's the group. That's the sample size for your first group, the group of workers. And you need to make sure there's a plus there, because that's what the formula has, right? Okay, so you found your mistake? All right. All right, so you see how easy it is to make a mistake on here. So you have to be very careful when you type. I am going to store this. So I'm going to use the STO key, the store key, and alpha E, so that I don't have to write down my margin of error. It's already in the calculator. So E is the margin of error. Okay, the other thing I have to do here is I have to find out what P hat 1 minus P hat 2 is. I need to find the difference between my sample proportions from the first group and the second group. So the first one was 192. (192 over 436 minus 40 over 121. So what I'm doing here is I'm subtracting the P hat 1 and the P hat 2. And so that's the difference between my sample proportions. All right, so those are the two things I'm going to copy over. Let me see if the large screen is better here. No, large screen does not look good for some reason. All right, so I'm going to move that over, and then I can work with this. Okay, so right now on your whiteboard, you should see the calculator. I know last time we were having trouble with that because it was taking a long time for it to transfer over. Are you guys able to see the calculator on the white screen, on the whiteboard? Okay, good. All right then, so let me just remind you what the margin of error looked like. The margin of error looks like this, and I'm just going to write something here just so that I have a value for E. So 0.080, and then that's a 49. 0.08049. All right, so I rounded it to 5 places. That should be safe. And so the formula has P hat 1 minus P hat 2. This is the difference in our P hats minus the margin of error. That's going to be my left side. And then P hat 1 minus P hat 2 plus the margin of error. And I already know what the margin of error is. It's right up on the top there. I already subtracted my P hat 1 and P hat 2. Those are these fractions right here. I've already subtracted those two. Remember we did that on the calculator? So this right here, that's P hat 1 minus P hat 2. Since I had the calculator up, I just went ahead and I found the difference between the sample proportions. That's the difference between the sample proportions. All right, so we're going to say, just because it was easy for me to round that way, 0.109788. So just easy for me to remember that. All right, so that's the difference in my sample proportions. Did I remember that correctly? Thought I did. Okay, looks good. All right, so minus the margin of error. Well, you already have the margin of error. It's up at the top. It's also in your calculator, right? So this one is going to give you the left, and this is going to give you the right. So your P1 minus P2, that will give you your estimate. All right, so let me just take you back to the calculator so you can just see what I'm doing. All right, so I have 0.109788 minus the margin of error, which it's already in the calculator. And then, so I don't have to type that all over again, I'm just going to do second enter. And then I'm going to change that minus to a plus. So that's what's happening on the right side of my confidence interval. So you have the left side and then the right side of your confidence interval. All right, so that's the left and then the right. So I'm going to go over to the whiteboard. And on the left side, we have, now I'm rounding it to 3 places, so 0.029. 0.029 on the left. And on the right, it was 0.190. Right, so let me just remind you what we had on the calculator. So this was the left side, and this was the right side. So I just rounded to 3 places. So that is my confidence interval, but it's a confidence interval for the difference in your population proportions. Not on the actual population proportion, it's a difference on it's the confidence interval for the difference, the P1 minus P2. So the way we interpret this is a little different than how we did it back in Chapter 7, where we're talking about one population, one sample. All right, so that was a lot of work, right, to use the formula, but you know how it works. You should know how it works in case I ask you to use the formula. But if I do not ask you to use the formula, then you can use your calculator. Whenever possible, you can use your calculator. All right, so let me go ahead and tell you what the command on your calculator is here. So this one, you're going to use the 2-prop Z interval, INT. So on your calculator, when you go to Stat, you're going to right arrow over to Tests. And then you're going to look for the 2-prop Z interval. You're going to type in all your values that we just wrote down from the problem, and then it's going to give you your confidence interval. So let's see if it works. So I'm going to take all this information here. And I'm going to clear what I have on the calculator here. All right, so this is how we would have the calculator construct the confidence interval for us. Now, of course, you'd have to decide what the appropriate command is in order for you to be able to get the right answer. So here, it's important to know how to identify your problem. So you wouldn't have to know that it's the confidence interval for P1 minus P2, because there's many confidence intervals. So you have to be able to identify the problem. So I'm going to go to Stat, and then over to Tests. And then I'm looking for the 2-prop Z-test. That's what I wrote on the whiteboard, I'm pretty sure. The 2-prop Z-test. No, I didn't write that, did I? It was the 2-prop Z interval, right? Because we were doing a confidence interval. All right, so my eyes always take me to the wrong place. So I have to kind of, kind of stop and think a little bit about this. It was a confidence interval. So it's the 2-prop Z interval, INT. So you have to make sure you're carefully looking through your options. And so sometimes it's just better to write it down before you look at the calculator. And there it is, the 2-prop Z interval. That's what I wrote down. Now, when you select the command, what you have on your window should look familiar because we've already written it out. Did we have an X1? Did we have an N1? Did we have all this information? Okay, so X1, I think that was 192. And then N1, that was 436. X2, that was 40. N2, 121. And confidence level, I believe it was 90, so 0.90. So it's just a matter of identifying X, N for both groups, and then typing in your confidence level. If you go over the word calculate, press enter, there's your confidence interval. How close is it to the one we have? All right, so ours was 0.029 and 0.190. Okay, and this is what the calculator gave us. Now, notice how the interval for our calculator looks a little bit different. I'm trying to put an arrow there so you can see it. Let me try something different. All right, so I'm boxing my confidence interval there, so hopefully you could see that orange box. So the way you'd write it is you have to make sure you're writing the difference between your two population proportions. 0.029 is on the left and 0.190 is on the right. So that looks like the same confidence interval that we got using the formula, right? All right, so on the final, when you come in and take the final, you'll use the formula if I specifically tell you to use the formula. But if the instructions do not say that you have to use the formula, then you are allowed to use the calculator command. The only thing you have to write, though, is you have to tell me what command you used. So in this one, let me just remind you, this was the 2-prop ZINT interval. So you have to tell me what command you used. Now there's no partial credit on these. Either you identified the problem correctly and entered in your information correctly, or you didn't. Of course, if you use the formula, I can see your steps. So for the calculator, you just have to make sure you're entering your values incorrectly. Make sure you're entering them into your calculator correctly. Okay, so what is very important on these confidence interval questions is what it means. What does this confidence interval mean? So when we're looking at the difference in our two population proportions, we want to know if our two groups are similar or if they're different. So is the proportion in our two groups similar or are they different? So we have to make a generalization about our population from the sample. So do workers and bosses have the same attitude when it comes to checking employee email, or do their attitudes differ? So are the proportions the same or are they different? Those are the things that I'm looking for when I look at confidence intervals for the difference between two population proportions. So the question you're asking yourself is 0 included? That's where we start. Is 0 included in your confidence interval? What do you think? So your confidence interval goes from a positive to a positive number, from one positive number to another positive number. So is there a possibility that 0 can be included if your confidence interval goes from one positive number to another positive number? Yeah, if you remember your number line, there's no way that's going to happen. If you go from a positive number to a positive number on your confidence interval, there's no way 0 can be in there. So just remember here the number line. 0 is in the middle, your negative numbers are to the left, your positive numbers are to the right. So if your confidence interval is only positive numbers, there's no way 0 can be there. If your confidence intervals are only negative numbers, then again, there's no way 0 can be included. The only time 0 will be included in your confidence interval is if one side is negative and the other side is positive. So there's a question about the second being smaller than the first. So remember, we're always writing down the lower one to the left. The smaller number always goes to the left on your confidence interval. And the higher number, the larger number, always goes on the right side of your confidence interval. So you have to make that adjustment. You always put the smaller number on the left and the larger number on the right. So I don't know if I answered your question. Is that what you meant? Okay. All right. So I had just used my space down here just to remind you guys about a number line, and now I'm deleting it. Okay. So in this case, we all agreed that 0 is not included. So you'll say no, it's not included. Okay. So then that means that P1 minus P2 can never equal 0. That's not even a possibility. If 0 is not included, the difference can never be 0. So P1 minus P2 could never be 0. If you move the P2 over to the other side, what that tells you is that they'll never be equal. They'll never be the same. So if 0 is not included in your confidence interval, then P1 minus P2 will never equal 0, which implies that P1 will not equal to P2. So am I saying that my population proportions are the same, or am I saying that they're different? All right, so the two population proportions are different. So from this sample, we're estimating that the population of workers and the population of senior level bosses, that their attitudes towards monitoring employee email, their attitudes differ. So the proportion for one is different than the proportion for the other. So in this case, there is a difference between the two groups. So we're 90% confident that we're 90% confident that the difference between the two population proportions lies between those two numbers. And so what that means is that there is a difference between the two groups. All right, so what I'm going to do here is I'm just going to type up a little summary at the bottom here. All right, so when 0 is included, when 0 is not included in our interval, then there is a difference. When 0 is not included in our interval, then there is a difference between the two groups. When 0 is included, in our interval, then there is no difference. All right, so when 0 is included, that means that one side of your confidence interval is negative and the other side is positive. That's the only way 0 can be included. Then P1 minus P2 could possibly equal 0. So if that's a possibility, then P1 could equal P2. So if P1 equals P2, then there is no difference. They're the same. The two proportions are the same. All right, so hopefully that little summary at the end will help you when it comes to answering the questions. Is there a difference between the two groups? All right, I was trying to make that a little bigger so you could see it. All right, so that concludes the finding a confidence interval for two population proportions, for the difference between two population proportions. So that is the end of section 9.2. In section 9.2, we were constructing confidence intervals for the difference between two population proportions, and we also, last lecture, we also did hypothesis testing when the claim was made about two population proportions. All right, so moving along here. That brings us to, so we're done with this one right here. So now for today, that brings us to all right, so I'm trying to circle something here. I don't know if this will work. There we go, boxing it. So now that brings us to inferences about two means. So now we're looking at inferences between two means. All right. In this case, the population parameters that we're looking at, it's going to be mu1 and mu2. So 9.2 was P1 and P2. We had two populations, and we're looking for and we're estimating the proportion from our population. Right, so we have P1 and P2. We have two populations, and we're making an inference about the proportion for each population. And then for 9.3, now we're looking at means from independent samples. So we have two different groups. Just like before, we had two different groups, two different populations, and we're making inferences about what's happening in our population. But we're making an inference about the mean for each population. All right, and then 9.4, which we'll probably not get to today. Maybe that'll be next lecture. But for this one, the parameter is the mean difference. So let me try that one more time. The D is a subscript there, the mean difference. So we're looking at the same group, but we take the before and the after situation, so you have data before and data after, and you find the differences. So if we're trying to see how effective a weight loss program is, you take your sample of individuals and you weigh them before the program, that's your before data, and you weigh them after the program, and that's your after data. So what you're looking at there is the differences between the before and the after. That's what 9.4 is about, where we are going to talk about matched pairs. 9.3, where we're talking about independent samples, you have two different groups. So if you're looking at a weight loss program, you have Jenny Craig and you have Weight Watchers. So one group is on Jenny Craig and the other group is on Weight Watchers. And so there you could look for the mean weight loss for the two groups, for your two samples. So that's independent samples. You have two very different samples. All right, so that's what I just talked about. Okay, so I am going to work under the assumption that mu1 and mu2 are unknown and they're not assumed equal. There's another scenario when they are assumed equal, but in this first part, we're saying we do not know what our population standard deviations are, and we do not know that they're equal. And so that if you're looking at somehow, if you have a population, you know that all of your, the population you're looking at, they all share something, or maybe you're dividing that group into two, but you already know that they're similar in some way. And so when you divide them into two, you regroup them. You know, that's one way you could assume that your sigma 1 and sigma 2 are equal. If for some reason you already know something about your population that you're sampling from, and you're going to divide it into two groups, then sigma 1 and sigma 2 would be assumed equal. But the most practical case, what would happen in real life is you don't know sigma 1 and sigma 2. You don't know that they're equal. Right? This is the more common situation. Okay, so again, we have samples that are independent. So we have two different samples. All right, so as far as the requirements, it's really the same as before. Well, one we just talked about. So two, the two samples are independent. Both samples are simple random samples. And then this condition about your data being normally distributed. So if your population is normally distributed, then there's no restriction on the sample size. But if your population is not normally distributed, then your sample size is greater than 30. It has to be greater than 30 in order for you to proceed. Right, so that's something we had already talked about. Okay, so we're going to start off with hypothesis testing. So if we're doing a hypothesis test for two means, and we have independent sample, this is the test statistic we use. So remember the one from where we had one sample? Just to remind you, back in Chapter 8, our test statistic looked like this. It was T, and then it was the mean from our sample minus the mean from our population. Well, that's the one that was under the null hypothesis. And then divided by the square root of S over N. I think that's what it was. I don't have my formula card with me, but it's right here. All right, so that it was our test statistic back from Chapter 8. All right, so I knew something looked weird. Okay, so let me go ahead and, the S was outside. All right, so hopefully that's what you guys remember. All right, there we go. And then there's a square root in there. All right, so that was our test statistic back in Chapter 8 where we only had one sample and where sigma was unknown. So it kind of follows the same pattern. So here it's the sample. This comes from our sample. So there's the difference in our sample means minus the difference in our population mean. So sample minus population. And then here we're taking the square root of our standard deviation squared over each of the two different sample sizes. Okay, so your denominator has to do with your standard deviation and your sample size. The bottom part is different though, because the square root is in a different place. So this is our new test statistic for when we have two different groups and we're testing, there's a claim about the population mean. Hypothesis testing for two means when we have independent samples. Now remember that when we do hypothesis testing, we're always working under the assumption that the null hypothesis is true. So when you set up your null hypothesis, we have the null and we have the alternate. This time we're comparing the two population parameters. In this case, they're population means. So you're always comparing them with each other. In Chapter 8, we were comparing them with some other value, but now we're comparing them with each other. So the null hypothesis has the condition of equality, and the alternate hypothesis would then have something else, the not equal to, the greater than, or the less than. So we're always working under the assumption that the null hypothesis is true. So what is the value of mu1 minus mu2? If the null hypothesis is true, what do I say mu1 minus mu2 is equal to? All right, so we say it is 0. Good, it's 0. All right, so that simplifies your formula a little bit, right? Okay, so that is our test statistic. And we are, obviously we're working with the t. You saw that was a t. So then the table we're going to be using is table A3. So when we have to calculate critical values or p-values, table A3 is the one you're referring to. We do have degrees of freedom, and you have two samples here. So you're going to have to decide which degrees of freedom to take. So the rule is that you're going to take the smaller of the two. So you're going to have two sample sizes. So you take the smaller sample size, and that's the degrees of freedom you use. All right, so here we have a problem, and we have to test the claim. Here it says test the claim that the distances come from populations with different means. So we have sample statistics for the distances of home runs hit in record-setting seasons by Mark McGwire and Barry Bonds. We want to use a 0.05 significance level to test the claim that the distances come from populations with different means. So we're testing the claim that the distances come from populations with different means. So here's a very important word here. different, they have different means. So it is the claim on the means. So anytime you see the word claim, anything that comes after it is a parameter. So here our parameter was mu1 and mu2. Because we have two groups and we have a mean for each group. If they're different, there's going to be a not equal to symbol in between them. And that is our claim. Okay, so we have 70 hits for McGuire, so that's our N1. And the sample mean for the 70 hits, that was 418.5 in distance. So I'm assuming, it doesn't have units here, but I'm assuming that's feet. 418.5 feet. Hopefully that makes sense. Okay, so 418.5 feet is the sample mean for the 70 hits. And so our standard deviation is 45.5. Now these are measurements, again, they're coming from that sample. And Barry Bonds, we have 73 hits. So our sample size is 73. And this sample mean is 403.7. So the average distance for the 73 hits by Barry Bonds, that was 403.7 feet. And then our standard deviation is 30.6. So we have our measurements for our first group and our measurements for our second group. So I'm going to call the first group the hits from Mark McGuire. So they're the hitting the distances, all the distances for the 70 hits. So if I actually had the raw data, I would see all of the distances for all those 70 hits. So there would be 70 data values that represent the distance that the ball made it to. And then my second group would be the distances for Barry Bonds. There were 73 hits, so my data value would have 73 distances. All right, so if you look at these two players, which one would you say is more consistent? Which player is more consistent with the hitting distances? What measurement would you be looking for? All right, the smaller standard deviation, right? The smaller standard deviation means there's less variability. So more consistent is Barry Bonds. But the one with the highest, at least for this sample, the one with the highest hitting, the one with the largest average hitting distance is McGuire, right? If you're just comparing these two numbers, McGuire has the highest mean hitting distance, while Barry Bonds has the most consistent hitting distance. But we can't just compare we can't just do a comparison from one sample to another. We have to go through the process of hypothesis test to make a generalization about the two players. So we're only looking at 70 hits here. We're only looking at 73 hits for Bonds. So from this sample, we want to make a generalization about them in general from all the hits they've had. And so what we see here could have just been by chance. If we randomly select another sample, maybe our results will be different. So we have to go through this process of hypothesis testing to see how we can use the sample to make a prediction about what's happening with the mu1 and with mu2. What's happening with the population mean. So mu1 is referring to McGuire, the average for McGuire, all of his hits, and mu2 is the average for all of the Barry Bonds hits, for all of the distance. When you measure all the distances and take the average, mu2 would be the average of all the distance. Okay, so this is a hypothesis testing question because it tells us to test the claim, and we're using a 0.05 significance level. So I am going to use the p-value method to make that happen. So the first step is to set it up. Remember the claim? Where does the claim go? Okay, so that means in the null, I'm going to have this statement on equality, right? All right, so we already know the test statistic. We have x bar 1 minus x bar 2. So it's the difference in the sample mean minus the difference in the population mean all over the square root of the standard deviation squared for the first group over its sample size and the standard deviation squared, which is our variance, for the second group over its sample size. All right, so that's the formula you're using, and we already said that mu1 minus mu2 is equal to 0 because we're working under the assumption that the null hypothesis is true. So you already know all of your values, x bar 1, x bar 2. You already know all that information because all that was given to us in the problem, and I made sure to label everything. Okay, so I already labeled everything. So I just have to plug all that in to the test statistic. All right, so go ahead and plug in that information and tell me what you get. Remember that this is a t, and so you are going to round it to 3 places. I'm just going to copy all the information from the previous page just so that you have it on this whiteboard. All right, good. So you have answers that agree there. So 2.273. Good. Okay, so that's our test statistic. And you rounded that to 3 places. 2.273. All right, so the next thing you want to do, if we're using the p-value method, is you want to find your p-value. Okay, so to find your p-value, you could use your table, table A3, but if you use table A3, all you have is an approximation. All right, so let me just remind you. If you're finding your p-value by hand, you're following this table right here. So what type of test is it? Look at the H1. I think our H1 was not equal to, so that tells us it's a two-tailed test. And if it's a two-tailed test, is the test statistic to the left or to the right of the center? So your test statistic was 2.273, right? So then you're on the right. Okay, so your p-value is twice the area to the right of the test statistic. So once you find one area, the probability is always the area underneath the curve. So once you find that one area, you multiply it by 2. Now you are at the advantage on table A3 that they give you the area for two tails already. So you just need to make sure you're looking under the right column for the two tails. So remember that if it's a two-tail test, it's the area for both tails. Okay, so what I'm looking, I'm going to scroll pretty quickly here, so you might want to turn away so you don't get dizzy. Okay, so those are my critical values for T. Let's see if I can trying to make that bigger, but didn't help. Okay, so let me just go ahead and move it over. Oh, that looks terrible. Okay, delete. I don't know what I was doing, but whatever I did, the table didn't copy correctly, so let me do that one more time. That's better. So right now on the whiteboard, you should see table A3. Is it there? So let me know when the table's on the whiteboard. I see it on my whiteboard, but there seems to be a delay. Last time there was anyway. Wow, that sure took a long time. Okay, so, but it made it. Okay. All right, I have to remember to stop talking right after when I see the table because I realize that there is a delay and you're probably not seeing the same thing I am. Okay, so remember that my test statistic is 2.273. Alpha is 0.05, but that is only important at the very end when you're comparing your p-value to alpha. That's when it's important. So all I need really is my test statistic. Okay, so 2.273. So degrees of freedom, well, I take the smallest sample size, which is 70, and I use the degrees of freedom. So that would be 69. So it's the smallest degrees of freedom, and that's going to come from the smallest sample size. So 69. So when you go to your table, you're going to look at 69, which I don't have here. Oh. Okay. But that's okay because I need the top portion. All right, so if you look at your table, is 69 on there? You can't see it on my table, but if you have yours, is 69 on there? It's not on there. Okay. Well, if it's not on there, what do I use? $69 is not there. 70 is the closest one, so we're going to use 70. Okay. Now I could go back and show you, but I need to refer back to the area up here. Okay, so remember that we have 2 point, our test statistic, whatever that was, 2.273. So we're going to have to look up 2.273 on that column. Now it's not this one, but wherever 70 is, you're going to have to find your test statistic. Now it's probably not there, but you have to go ahead and look at the closest one. All right, so I'm going to go to, again, to the table. All right, so there's a table again, and I'm just going to scroll down so I can use 70. There it is. And then I'm going to copy it over to the whiteboard. Okay, I don't know why that's happening. Delete it. The table is broken when I get over, so I don't know if I just have to do it slower. That's better. So right now, you should see the table on the whiteboard. And what I'm doing is I am boxing the row of numbers that correspond to 70 degrees, or 70. We didn't have 69 degrees of freedom, so I'm using 70. So do you see the box around the row that corresponds to 70? Okay, there it is. All right. So remember, our test statistic is the one that you typed out. Let me go back. 2.273, 2.273, 2.273. Let me write it out. 2.273. All right, that was your test statistic, and 2.273. It's not on here, but if you notice, as you're moving in this direction, as you're moving from right to left, your values are getting larger, right? And so you can kind of estimate that 2.273 is probably going to be right here. It's in between it's larger than 1.994, but smaller than 2.381. Do you agree? All right, so it's larger than, or let me rewrite that. I have the wrong inequalities. All right, so that's all we can get. From our table, all we have is an estimate. So it is greater than 1.994, but less than 2.381. So I just reversed the numbers because the smallest one has to be on the left side, the way that I wrote it. Okay, so then what I'm going to do is I'm going to go up to the top, very top. So I'm going to have to go to my other screen. So what I'm doing is I'm going to the very top to see what area that corresponds to. Because that area, that's my p-value, that's my probability. So the test statistic is in between those two values. So what do those two values correspond to as far as areas? So let me go back. So just keep in mind that it's the second and the third column. The second and the third. So the second and the third. So if we're continuing on the second and the third. So these are my arrows coming up to the very top from the second and the third. All right, so we had a two-tailed test. So we had the area in two tails. So that means that my p-value is in between the two that are there. So my p-value is in between. Now I have to make sure the smallest is on the left. So I have to rewrite this. So 0.02 or 0.05, which one is the smallest? So that's what I have to look at. Okay, so 0.02 is the smallest, 0.05. So from the table, that's all I can just give you an estimate. P-value is between 0.02 and 0.05. On the calculator, you can get an exact value. So let's go ahead and compare the calculator with what the table gave us, and then we can see if we're okay, if we can confirm it. All right, so on the calculator, that's our third step here, our p-value. For this one, you are going to, there are a couple of ways you can do this. Since you have sample data, or well, we have sample statistics, right? Since you have sample statistics, you can use the two-sample t-test. You can use the two-sample t-test. If you didn't have sample statistics or sample data, then you would have to find the p-value using the t-CDF. And we talked about that not too long ago. So the t-CDF command, you would use it if you only are given the test statistic. And well, we have the test statistic here, so that shouldn't be a problem. We can use that test statistic. So, so you have an option. I think the easiest and the fastest way is to just use the two-sample t-test. So that's what I'm going to show you. Okay? All right, so for this one, you're going to use the two-sample t-test. There's a lot of information here too. There's just a lot of information to keep in mind. And so if you look at your lecture notes, I created a Chapter 9 summary for you. And it has all of your formulas on there with the corresponding calculator commands. So I'm just double checking to make sure that that's on there. I'm saying it is, so let me check to see. I'm pretty sure it is. Let me. Okay, somehow that did not make it there either. Okay, oh no, it is. It's at the very bottom. Okay, I'm having trouble with bringing this whole thing up to the very. No, it's not. Okay, so I need to make sure that that's on there. But let me show you where you could find it. It is there. It's just not under lecture notes. Okay, so here's your Chapter 9 notes. If you go to announcements, that final exam study guide that I showed you last time, that's where you have all the summary, all the chapter summaries there. You just have to scroll all the way to the bottom. So that study guide, that starts like that. That has all the summaries on there. So if you go to Chapter 9, that's what I'm referring to. All right, so I'm going to take a snapshot of that. And so I break it down. Either you're talking about testing a claim, which you would do a hypothesis test, or I'm looking at confidence intervals. And so all of the formulas are there, and they match up with the parameters. And then on the last column, you have calculator commands. Okay, now you can't see it on the whiteboard, you just see kind of an outline of it, but you'll see it on the document, all right? So it's just organized for you, so you know which calculator command to use. All right, so make sure you take a look at that. It helps you organize everything. All right, so then I'm going to go ahead and open up the calculator, and that's the two-sample t-test. All right, so don't forget all that. I'm going to go ahead and need all of this to put in there. So back to the calculator, and I am clearing what I have here. Okay, so I'm going to go to Stat, and then over to Tests, right arrow to Test. And remember, I'm looking for the two-sample t-tests. That's number 4 on my calculator. 2 sample t-tests, and then I pressed enter. So either I have data or I have stats. If I have the actual distances for all of the hits, if I had the data values that represents the distances of every hit, then I would have data and I would put it in L1 and L2. But I didn't have that. I just had stats. I had my sample statistics. I had the mean and the standard deviation. So this window should look similar to what the information that we already had. So we have the mean for the first person, so that was McGuire. So McGuire had a mean hitting distance of 418.5 and the standard deviation of 45.5. And then the sample size, that's the number of hits, so that's 70. And then we had Barry Bonds with 403.7. That was the mean distance. And then the standard deviation was 30.6. And I need to make sure the sample size, I didn't see the sample size, that's 73. All right, so you just have to make sure everything was entered correctly. It's very easy to make a mistake here. And then for the H1, what was in the alternate hypothesis? You have to decide what we had in the alternate hypothesis. Do you remember? All right, so it was not equal to? Okay, so then you select the not equal to and then press enter and it highlights that for you. Okay, so use your arrow key to go down or you just press enter. Okay, so now we have this question, is it pooled, yes or no? When your sigma 1 and sigma 2, when your population standard deviations are not assumed equal, which was our case, then we say no to the pooled estimate. And later on we'll go over to see what a pooled estimate is. But for right now, when sigma 1 and sigma 2 are unknown and not assumed equal, we say no to pooled. And that's usually the default. So if the problem doesn't say anything, then this is the default, that we say no to pooled. Now, the only time it would be yes is if the problem specifically says that sigma 1 and sigma 2 are equal. If somewhere in the problem it says that sigma 1 and sigma 2 are equal, which are the population standard deviations, then that's the only time we choose yes. Okay, so go over the word calculate, press enter. And so look at the test statistic. Remember, you found that by hand using the formula. So there it is again, 2.273, I think is what you found. And then our p-value is right below it. All right, so I'm going to compare this p-value with the one we got using the table. So I'm writing it down, 0.0248. Don't forget that. All right, so that is what I'm writing here for the p-value. And you have to write down how you got that p-value. So I wrote down the calculator command. So the p-value is equal to 0.0248. That is our p-value, and I got it using the 2-sample t-test. Now remember that I used the table over here. So that was an estimate that the p-value from the calculator was equal to 0.0248. So was our estimate correct? That's just an estimate from our table. So 0.0248 is between 0.02 and 0.05. So the calculator gives you the exact p-value. The table just gives you, an estimate. It's just in the ballpark. It's an estimate. All right, so whenever possible, you're going to use the calculator. The only time you're going to use the formulas is if I tell you specifically to use the formulas. And so what I'm doing here is I'm showing you both ways. You should know how the formulas work. And if I tell you use the formula to find the test statistic or find the p-value by hand, you should know how to do that. But if I do not tell you anything about how to do it, then you could use the calculator, since that's the quickest way. So the hardest part in all of these word problems is identifying the problem. So by identifying the problem and knowing how to continue, if you can do that, then that's already, that's the hardest part. So the rest is just, making sure you can plug in numbers. So the hardest thing is identifying the type of problem you're looking at and knowing what the correct process is. All right, so then if we're using the p-value method, the way we decide what to do with our null hypothesis is we look at our p-value, and if it's less than or equal to alpha, then we reject the null hypothesis. So I'm just going to write that down so we don't forget that. So remember, if our p-value is less than or equal to alpha, then we reject the null hypothesis. Now, was that the case here? So our p-value, 0.0248, and our alpha, I think alpha was 0.05, right? All right, so definitely less than alpha. So yes, we're rejecting the null hypothesis. Okay, and then the rest is just going back to the same conclusions that we've been looking at. All right, so you start out asking, does the original claim contain the condition of equality? So remember, the claim was that the mean distances were different. So that was not in the null hypothesis because it had the not equal to. So no. The claim was in the alternate. Now, did we reject? We did. Okay. So the third box, that's your conclusion. All right, so I'm just going to type that out. I'm just going to reread the question. It says, test the claim that the distances come from populations with different means. So the sample data supports the claim that the mean distances are different. And let me make sure that it's written exactly the way the problem is. Test the claim that the distances come from populations with different means. And I went back to the problem. I just copied how it was phrased. All right, so the null hypothesis was rejected. Remember, we're always working under the assumption that the null hypothesis is true. So this is where I have to go and cross out the null hypothesis because we just saw that it was not, we don't assume it's true anymore. So we have evidence that says otherwise, and so in this case, the claim is what's supported. The sample data supports that claim. So I did a lot today. I went ahead and I showed you how the formulas worked, and you also have the option of doing that on the calculator. And I would use the formulas a couple of times on the homework. But once you know how to use them, then make sure you're doing these on your calculator because it does save a lot of time. And that's not a lot. You don't have a lot of time on the finals, so you want to make sure you can move through problems quickly as well. So learn how the calculator works. All right, so the next example that I have, the last one for today, well, I think I might have a few formulas just to talk about. I don't know if I'll get to another example, so we'll see. Oh, and then this one, this is just a box plot of the data for the distances. And so you see that Barry Bonds, look at the box plot for Barry Bonds. It's a lot shorter. So that's what we're talking about, more consistency. But if you look at the median, I think McGuire's median hitting distances, that's the middle of the, or that's the mark that looks like in the middle, that was higher than Barry Bonds. But the shorter box plot, that's talking about it's less variability, so more consistency. All right, so this is the one we just worked out. It's just all typed up there. Okay, so now we're looking at confidence interval, and there's a very important correction I need to make here. And that correction has to do with this value right there. If sigma 1 and sigma 2 are unknown, if our population standard deviations are unknown, we don't work with these. That's supposed to be a t. So that's t alpha over 2. So first of all, make that correction. And so if we're working with the t, that means we have our sample standard deviation. And that's what you see in the formula here. You have S. So the sample standard deviation is given, of course. Here you use the variance because S is squared. That's our variance. But on the calculator, this is your 2 sample. I was trying to get a darker color. Didn't happen, so let's try again. So our calculator command for this is 2 sample. And I know the word sample isn't actually spelled out. I think it's S-A-M-P or maybe S-A-M. Let me check. S-A-M-P, okay. 2 sample, and then this would be T interval. T, and it's I and T. Now remember that we are assuming that sigma 1 and sigma 2 are unknown. And they are not assumed equal. They are not assumed equal. So when you get to the question where it's asking you for pooled, you're going to say no. There is, I think, one example or one homework problem where it says sigma 1 equals sigma 2. So if it tells you specifically that the population standard deviations are equal, then you say yes to pooled. Okay, so when you're using this confidence interval formula, it's going to be a 2 sample T interval. So again, I organized all this on that study guide that I showed you under announcements. So if you go under announcements and if you scroll down all the way to the bottom, you have it's called study guide. Yes, it's study guide for your midterm. So that's where I ended up getting all those formulas for Chapter 9. All right, so here we have to construct a 95% confidence interval. So I'm going to spare you using our table. I mean, I want you to do it to make sure that you can use the formula. So I'm going to spare you using the formula. I'm not going to do that. We don't have enough time. But I want you to use the formula. I want you to work it out to see if you can go through it. I mean, it's just a lot of plugging in. You know all of your information, so it's just making sure you plug it in. Make sure you make the correction. It's a T, not a Z. So you're looking at table A3 when you're finding your critical value for the formula. Okay, so here we're constructing a 95% confidence interval. Notice the data, it's the same information as before. So just to make things go faster, so we don't have to read a different problem, I'm using the same data from before. But now I'm constructing a 95% confidence interval. So I'm going to go back to the calculator. All right, so here's the calculator on your screen. Hopefully you can see it. I'm going to go to Stat and over to Tests. And I'm looking for the two-sample t interval. Now, there's the two-sample t-test, but that's only for hypothesis testing. And that's not what I want, so I need to continue. It's the two-sample t interval, INT. So there it is, t interval. I'm going to select that. All right, so the nice thing about this is since we already did the two-sample t-test with the hypothesis testing question, look at what happened. It remembered our information. Now, does your calculator have the same thing? Okay, so that'll save us some time, right? You don't have to enter anything. It's already there. Since we did the two-sample t-test for the hypothesis testing question, it remembered all that. So now we're at two-sample t-interval. So we're doing a confidence interval. So just scroll down using your arrow key. Scroll down. I have to change the confidence level to, I think it was 95, so 0.95. So I already had a 0.9 there, so I just made it 0.95. And then if you scroll down, if you use your down arrow key, now it asks you about whether or not it's pooled. So the default is that sigma 1 and sigma 2 are unknown and not equal. So you would select no. Again, on the homework, I think you have one where it says sigma 1 equals sigma 2. They are equal, so you'd have to choose yes. But for this one, it's no. And then over the word calculate and just press enter. And what you're going to see there, that is the confidence interval for the difference between your two population means. All right, so I'm going to copy this over to the whiteboard, and I know that takes some time, so tell me when you see it. All right, thank you. Okay, so now the calculator doesn't have the parameters there it just gives you the two numbers, the lower and the upper. So you want to make sure that you're using the correct parameters. This was the difference between your two population means. So the smaller number goes to the left, so I'm going to round that to 1.91 and then 27.69. All right, so if what you would do here is you tell me what you did. This was the two-sample t-interval, T-I-N-T. So I used the calculator, and that's my confidence interval. If you use the formula, I want you to try it on your own. If you use your formula, your confidence interval is going to come out a little bit different because you're using a critical value, and the critical value came from table A3, which, by the way, happens to be rounded values. So the critical value from the formula was rounded. So that gives you a different interval. So that's 1.82. So when you work out the formula, make sure you're getting these values. All right, so 1.82 and 27.78. And just so that you have it, the T critical value that went along with the 95% confidence, that was 1.994. So that's just a reference. If you don't get the same confidence interval, just make sure your critical value is correct. Okay? All right, so the interpretation is what is very important with these confidence intervals. Remember, it's a confidence interval on the difference. So either the two groups are the same or they are not. So in this case, we had hitting distances for McGuire and Bonds. So either their mean hitting distance are equal or their mean hitting distances are not equal. Either they're the same or they're different. So what you do is you look to see if 0 is included. Is 0 included in these confidence interval? What do you say? Okay, 0 is not included because it goes from a positive to a positive. No way that 0 can be included. So does that mean that the means are the same or that the means are different? Are they the same or are they different? All right, so they are different. Good. So mu1 minus mu2 could never be 0, of course. Let me write it on the side. So mu1 minus mu2 does not contain 0. Therefore, they cannot be equal. So if they're not equal, that means they're different. So there is a difference between the two means. So no matter, it doesn't matter whether you use the formula or the calculator command, you still get a confidence interval that does not include 0, so your conclusion would be the same, right? So you're 95% confidence that the difference between the mean home run distances of Mark McGuire and Barry Bonds, we're 95% confident that our estimate is between those two values. So remember, it's the mean difference, not an estimate on the actual mean, but it's an estimate on the difference of the means. So what you're saying is you're either telling me that the means are the same or that they're different. And it all depends on whether 0 is included or not. So watch out for those kinds of questions on the Chapter 9 homework, and I'm just going to check to make sure your Chapter 9 homework is here. I can't remember if it is. Yes, it is posted there. Okay, so it is posted there. And today's lecture, which I just saw okay, so today's lecture, which is number 21, make sure you go to the homework tab on My Stat Lab to find that. Now I noticed it didn't pop up on there, so I have to make that available. That'll take me a few minutes. So I've already printed out the participants list for those of you who are attended. And so just wait for a few minutes. I need to make that come up. So don't forget to do the lecture problems. And it should be short, and you can use your calculator for the problems I'm putting there. Okay? All right, I'll talk to you next time.